Good morning, good afternoon, everybody, wherever you listen and watch. I'd like to talk about the role of human mobility in epidemics and studies of epidemics, and also on the control of epidemics. Let me start with, no, I'm in the wrong window, sorry. Let me start with 3 examples of coronavirus epidemics, which show that the severity of an epidemic increases drastically as it becomes transmissible, as the pathogen becomes transmissible between humans. And this has happened with the first SARS coronavirus disease, where the disease was more or less endemic among bats. It became transmissible among civets and then between humans. Case fatality rate was 10%. Then next important coronavirus example, MERS, which started in 2012. Another outbreak in 2015 in South Korea and some other places also. Again, the reservoir was in bats. The virus was transmitted and mutated and was able to be transmitted between dromedaries, and then it moved to humans. Basic reproduction number 2 to 5. This is not very special, but the case fatality rate 40%. That's extremely high. Now, the present SARS coronavirus disease again started in bats, was transmitted probably to pangolins. Some people argued perhaps snakes, and finally could be transmitted between humans and among humans. The incubation period is 1 to 14 days. The onset of symptoms is on average after 5 days. The basic reproduction number, was between 2.4 and 3.3. It's now smaller, of course, after the containment measures. Case fatality rate, not so high, actually the smallest among all these cases. But nevertheless, it's the most dangerous we've seen so far. And the reason for this is what I marked in red. I don't know whether you can see my arrow. The incubation period is between 1 to 14 days, on average about 5, 6, 7 days. But the onset of symptoms is after 5 days or so. That means that you can be contagious before you notice any symptoms, and you can transmit the disease. So that's the reason why it's so dangerous. But let me come back to the question here. In all these 3 cases, the severity of this epidemic increased very drastically as it became transmissible between humans. So that points to the effect of spreading by human traffic, because a virus can spread much more efficiently among humans through the human traffic. And it's very important to understand the statistical properties of human traffic if one wants to understand and control the spreading of an epidemic. This is the classical picture, let's say, of an epidemic among animals, or where each animal has a home range. And these home ranges of different animals overlap, and thereby a pathogen can be transmitted from one individual to another one. this is how it works in animals, and it's extremely slow, of course, compared to the human transmission. This is how it worked maybe in the 14th century. What you can see on the right-hand side, where an epidemic was spreading more or less like a wave front in a diffusion front in a reaction diffusion equation. But our home ranges have changed. And here you see our modern home range, or home ranges. This is the International Aviation Network. And color-coded is the intensity of transport. High intensity is in light colors, and so on. And so within a day or two, we can reach almost any place in the world. And our home ranges have become very large. And this has changed the whole situation. And this became clear, I guess, for the first time during the first SARS epidemic. That the aviation network played an important role in the spreading of the epidemic. And this is what I want to show in the first part of my talk. In the second part, I will ask the question, is it possible to assess human mobility, for instance, using a proxy, introduce this Levy flight model, and finally also deal with cell phones as proxies. Let me mention my main co-authors, Dirk Brockmann, who is professor at Humboldt University and leads a group at the Robert Koch Institute in Berlin, our German CDC. Lars Hufnagel, who's leading a group at the European Molecular Biology Lab in Heidelberg. The first SARS disease spread from Guangdong in China, but there's not much known about the early stage, except that it arrived in Hong Kong, and there was an outbreak in Hong Kong from where it spread to various countries, actually many countries. As I said, it was clear that the aviation network played a role. We modeled this first with a local infection dynamics, where we used waiting time distribution for instance, the waiting time between the infection and the onset of symptoms, and then a waiting time distribution for the time between the onset to the admission to hospital, and so on. This is the local infection dynamics. Actually, here on the right-hand side, you can see the exponential increase in Hong Kong. We coupled this local infection dynamics with a spreading on a network where the nodes of the network were metropolitan areas I and J, and NI and J are the populations of in these metropolitan areas surrounding an airport. And we measured the intensity of transport between two such areas by the aviation, the intensity of aviation transport, passenger transport, described by these matrices MIJ. Here you can see it again, the network of aviation movements, color-coded again. So this is, in short, the model we used, and we used an agent-based simulation. And here's a a comparison of the actual data after 90 days and the simulation after 90 days after the outbreak in Hong Kong. Color code is down here underneath, and you can see that one can relatively well predict the spreading of the epidemic, at least in those 3 months where the spreading occurred mainly on the aviation network. Okay, now I have to stop this here. Okay, my microphone was gone. Okay, I'm back. So there are of course fluctuations. Like Canada actually had more cases than predicted, and it was one of the earliest. Toronto, I think, was one of the earliest hotspots that was reached from Hong Kong. So this can always happen. Oops. One can study various things. One can study containment strategies, closing an airport, closing connections between airports, and so on. This is what we did in this paper. But let me just mention one thing. One can see easily that by looking at this figure on the left, which shows the infection time for the 10% largest cities in the world and for the other cities in the world. And one can see that the distribution of infection times is peaks much earlier in the largest cities than in smaller cities. So there are different spreading mechanisms, and this shows that the large cities trigger infections or trigger the further spread of an infection. And this can give us information on vaccination strategies. Okay, let me skip the structural properties, the connectivity, and so on. There's a strong variability. Let me show this. There are, for instance, Frankfurt is a strong hub with a high connectivity. Chicago has many more passengers per day, but has much less connectivity. Now, this was epidemic spreading on the aviation network, but of course, modern travel occurs on all length scales. Let's say from bikes, pedestrians to aviation transport. So how can one assess the statistics of this transport on all scales? There in the US, there is the National Bureau of Transportation Statistics, which has provided statistics, but they essentially asked people in the street or in train stations, where did you come from, where are you going to? And so like this, you don't get really big data. So we have asked some time ago, can we use a proxy to do this? And I think we were the first to use a proxy to assess the statistics of human mobility. And the proxy we used was to follow the money. An advice that was given after the Watergate scandal. Some elderly people might remember this. So back to the United States. Another US president found on this $1 bill. But here you can see track me at worstgeorge.com. Currency tracking project on the right-hand side. So Americans have started stamping their dollar bills and reporting where and when they got a dollar bill on this website, Worst George. And so they report the place and the time where they found this dollar bill. And then there are somebody else reports later on the same dollar bill in a different position. So like this, we got more than 11 million trajectories. Afterwards, we got many more. And but you cannot make use of these trajectories because you don't know whether the dollar bill traveled in between these two reports, especially when the time difference is large. But of course, there is a simple trick that you can use and which we used. We only filtered out such events where two reports were given within 3 days or less. And those are shown here. So like this, you can get individual trajectories among different cities in the US, between different cities, sorry. And here's a distribution of these short-time trajectories. You can, in log-log, you can see an inverse power law decay, like here expressed on the right-hand side with an exponent 1 plus beta, where beta is 0.6. This is, if it tends to infinity, it does not have a mean, it does not have a variance. So in a sense, it is scale-free. It's a scale-free distribution. That's what I expected. Now, this is not the whole story. Here is this was a super diffusive effect after a time t. Then you see that this kind of survival probability also decays in an inverse power law with an exponent alpha also 0.6. And so this is a diffusive process. We modeled this very analogously to what I modeled, I don't know, more than 30 years ago. It's been called Levy walk afterwards. We modeled the following process. A dollar bill can jump a distance delta x, or let's look at this, and they then stay at this position for a time delta t, and then jump again. And both of these jump length and waiting times have an inverse power law distribution with different exponents in principle, although they turn out to be the same. This kinetic model leads, when you treat the theory, leads to a bifractional dynamics in some kind of diffusion equation. This is like a Fokker-Planck or diffusion equation, what you see here, but it's a bifractional equation. It has a fractional derivative with respect to time, and it has a fractional Laplacian with respect to space. And we can solve this model and show that the solution has a scaling behavior where the probability of finding the dollar bill at a distance x from its origin at time t is a scaling function that depends on this distance x divided by t to these two exponents, alpha over beta. And again, this is scaled by 1 over t to the alpha over beta. This can be checked with the full data set. The model was based on the filtered data set, but this is now checked. I guess if I don't continue, I'm running out of time. So let me be short. The usual data collapse that you can use to check a scaling function on the right-hand side As we scale x and we scale the probability p, we find the data collapse for events between 10 and 365 days. So that demonstrates the scaling property of this solution. And we can also calculate this function L analytically. The last step is done by a Fourier transform, and that's shown here and actually fits quite well the data. So let me resume this. Spreading occurs in a simple diffusion law, but it's a bifractional diffusion law. And the distance traveled goes like linearly in time. To come to an end, let me mention other proxies. Of course, we thought about using other proxies that might be even better than dollar bills, like credit cards, for tracking credit cards or tracking mobile phones. This was very, of course, a very sensitive topic, and we couldn't imagine that it was possible to get data in those days. Nevertheless, the Barabashi group managed to convince a telephone company to give them mobile phone data. This also caused a little uproar in the community afterwards, but nowadays this is no longer, nobody understands this anymore because we need such kind of data. Of course, there are security issues and data protection issues that we have to follow. This is extremely important. But using such data is a means to help us now in this situation. So on the right-hand side, again, you see the power law behavior for the jump length of a trip. On the left-hand side, one sees by looking at individual motions, one sees that 80% of the time of a user is spent in two locations, like maybe at home and at work. So we have recurrence effects to sites that were visited. And this can be included in the models also. Let me go to my last slide. Back to the COVID-19 disease. Of course, now we are waiting for Google and Apple to give us this decentralized apps that will allow us to track, well, not to track humans, but to give us the information on meeting infected. But this is a different question here, what I'm showing. Dirk has, yes?
Can you conclude?
Yes, this is my last transparency.
Okay, thank you.
Okay, this transparency shows the change in mobility in Germany. It essentially shows the number of trips that were tracked by mobile phones between cell phone areas. And so a trip is when you change from one cell phone to another cell. And it shows a decrease in mobility from February to the end of March. It's a decrease of 40%. And then one can see that there is a slight increase. People start traveling more and more again. And so this is one of the possibilities where it can be useful, and it's already used, because as the mobility increases, we can expect that R0 will start increasing again. And that's the end of my talk, and here's my outlook. Thank you for your attention.
Thank you, Theo.